Well, good morning, everyone. Thanks for attending our webinar series. This is the Mallett Technology webinar series that we've been doing every Friday here for the past few weeks. My name is Boz Marshy. I'm the Technical Account Manager here at Mallett Technology. Our presenter today for our webinar is Steve Rugg, and Steve is the Technical Services Manager here at Mallett. Today's agenda, a quick overview of the company. Then Steve will give us the fatigue and weld assessment in ANSYS webinar. And then at the end, we'll have time for discussion and questions. I will unmute at the end so you can ask questions. Also, if questions come up during the webinar, or if you just want to type them in, you can do it at any time in the chat section of the GoToMeeting box. So either way, you can just type your questions in or ask them at the end of the meeting. Mallett Technology uses world-class engineering software tools combined with a broad knowledge and expertise to help our clients compete in today's marketplace and produce reliable and effective products. A quick overview of Mallett. We've been serving customers for over 40 years. We started as a consulting arm for Swanson Analysis Systems, which later became ANSYS. So we were founded by the same person, Dr. Swanson, in the mid-70s. We've been an ANSYS channel partner since 1995. You can visit us at www.mallett.com, of course. Like I said, we've been doing these every Friday. Our next webinar will be on meshing. I know that's a subject that a lot of people have questions on. So next Friday, the subject will be meshing, and that will be at the same time, 11 a.m. Eastern. We're also doing a live classroom training on it's ANSYS basic structural nonlinearities, which is an advanced class in ANSYS mechanical, and that will be here in our Durham, North Carolina facility, November 14th and 15th. And everyone should have gotten who's on the webinar list should have gotten an invite to this live training. So if you're interested in that, just let me know. You can give me a call or email at info@mallett.com. You can always contact us there. And that classroom training is 2 days, and it should be interesting. So if you are interested, please let me know. Now we'll get started on the webinar. So I'll give Steve control. And Steve, if you'll go ahead and get us started, we look forward to the webinar on welding and fatigue. Thanks.
Okay, sounds good. Yeah, so just a brief introduction. I know Bob's already introduced me, but I'm the Technical Services Manager here at Mallett. Really what that means is the majority of my job is consulting engineering, just for our various customers. And then additionally, I have some other responsibilities. So generally, you can look at me as a consulting engineer. I'm typically working in ANSYS all day, every day, particularly on structural dynamic simulations. So today we'll talk about weld modeling and stress and fatigue evaluation. Specifically, I'm going to look at the what quote unquote is the Mallett method. This is also similar, if not interchangeable, with the nominal stress method for evaluating welds. And so one note here, weld stress and fatigue analysis is an incredibly wide and varied field. There's a lot of different methods that are in use today to try to evaluate welds accurately. I'll touch on a few of the methods, but I'm really only going to go in depth into how we do things here at Mallett. And while I am well versed in our approach and the rationale behind it, I would not necessarily qualify myself as a welding expert. My expertise lies in FEA analysis and how to analyze welds from that perspective. Okay, so quick background. As I'm sure all of you know, welds are commonly used to join components together in structures. Weld failure can often be catastrophic and costly. I have a couple of pictures to show. Welds are often weak points in structures, and they are, from a FEA perspective, they can be one of the most challenging portions of the structure to make a strength assessment on. So simulating welds and properly interpreting the stress is a non-trivial activity. Like I mentioned, there's many different methods to do this, and I'm going to talk about the Mallett method. So just a few notable weld failures. So you can see on the left side of the screen, this is a wind turbine failure. Essentially, the weld failed. There's a weld essentially 30 meters off the ground, and a crack propagated along the weld line. And so you can see that entire tower, so it's a 100-meter wind turbine, from 30 meters up just toppled over. And then in the top right-hand picture, we have a oil rig. In the lower structure of this oil rig, I ended up seeing a small weld failure on one of the primary supports. That weld failure propagated to the entire oil rig capsizing, and unfortunately there was around 200 deaths in that incident. In the bottom right, we can see another case where we have a weld failure causes an entire bridge section to collapse. That occurred in China. So, I mean, arguments can be made that also there's been catastrophic failures as a result of bolt failure or gasket failure or any number of other things. But since we're focusing on welds, I figured I would show some weld examples. Okay, so why are special weld analysis methods necessary? So really the primary reason is that weld strength is not as easily quantifiable as metal strength or metal stress. So when we look at metals, right, whether I'm talking about, let's say, 304L stainless steel or A36 steel, or any number of different steels, generally the strength is repeatable no matter where the steel comes from. Typically, there's a defined material composition for each metal, and this really drives and dictates the strength of that metal. Additionally, we can get very accurate stress approximations with FEA tools that allow us to quickly categorize whether or not a structure is sound or if there's risk, right? However, for welds, weld strength is dependent on many factors, right? One of the biggest is welder skill. This is typically one of the reasons welds are often inspected after they're initially made, right? We have many different kinds of inspection methods for welds. There's visual inspection, which is just looking at it, it's kind of the most cost-effective. Radiographic, liquid penetrant inspection, and a number of others, right? In general, when we're inspecting the welds, we don't often inspect, let's say, the base metal in an area far away from machining or bolt holes or things like this, because generally we trust that the metal was made well and made to standard. So with respect to FEA analysis, it's pretty much impossible to represent welds without creating stress singularities. There's almost always a right angle or a hard termination when welds are modeled, right? And so what this means is if we're looking at welds on a stress plot, usually the stress results are masked by the presence of these singularities. So then you could ask the next question of, okay, so is there a way to explicitly model the welds and get stresses maybe away from the singularities that are accurate? So if we explicitly model the welds, the next challenge becomes generally welds are much smaller than the size of the entire structure. So if we're modeling the welds, we have to mesh them finely enough to get an accurate stress, and meshing them that fine can often make a solution or simulation prohibitively large. So that's a drawback, right? And then our third option would be, okay, is there a way to abstract the welds, rather than representing them. But if we abstract welds, this results in you still get some stress singularities, but also results in non-real stresses at connections. For instance, if I have like a T-junction between two metal plates and it's welded on both sides, if I abstract the welds, so essentially I just join the two plates together rather than representing the welds, and I look at the stress at that joint, that is no longer real because the presence of the weld in that actual structure would impact the stress in that region. So we can no longer, if we abstract the welds, we can no longer just look at a stress plot and say, okay, here's the junction, this is the stress. We need an additional method to get accurate weld stresses. So in terms of methods to use once we kind of run our simulation, there's several. I'm just going to touch on them. So the primary one, which I'll go into detail, is nominal stress method, and this is primary for Mallett. So in this method, essentially you extract forces and moments at a weld interface, and then you post-process these forces and moments to calculate the weld stress. And then there's various standards out there that define allowable stress values. A second method is called the hotspot method. Essentially here you look at stresses certain distances away from the weld toe, and you extrapolate the stress at the weld toe from those stresses, right? Essentially, you're trying to get rid of the impact of the singularity that likely exists at that toe in the simulation. Third method is the notch stress or effective notch method. So this predicts service life that will pass if cracks nucleate in certain locations. Once again, I am not well versed in this method. So if you're more interested in it, feel free to take it up. A similar method to that is the fracture mechanics method. This assumes certain cracks at the weld toe, and then based on the loading, it will make a prediction on how quickly those cracks will propagate and eventually cause failure. There's a stress linearization method. This is more relevant for like ASME blow and pressure vessel code, where you would linearize the stress at a weld toe and then increase it by a specific factor usually dependent on the type of weld it is, as well as the inspections methods that were done on it. Essentially, ASME says if you don't inspect it sufficiently, we're going to penalize you by having that weld stress increased further. So you have to design with more conservatism. And then 6, there's many others, right? It's a very wide and varied field. Okay. So nominal stress approach rationale. So by default, ANSYS is going to calculate forces at nodes of solid elements. All right, solid elements have 3 degrees of freedom, translation X, Y, and Z, and they're going to calculate forces and moments at nodes of shell elements because shells have 6 degrees of freedom, translational and rotation in each direction. And so the nominal stress approach essentially extracts these forces and calculates the average weld stress from those forces. The benefits of this approach. So first, a relatively coarse mesh can achieve accurate forces and moments. It's well known that in finite element analysis, it's much easier to converge stiffness than it is stress. And forces are related to this stiffness convergence. So we don't necessarily have to worry here about refining a mesh until that mesh is converged, especially if it's impossible to converge because there's singularity. We can just run with a relatively coarse mesh and extract the forces accurately from that level of refinement. Second pro, so the results of the forces and moments are not impacted by FEA singularities, right? Generally, we see stress singularities because you have a force or a load applied to, let's say, a 0 area. So you essentially get 0 in the denominator. As you refine the mesh, stress goes to infinity. Or you have a right angle or another number of other cases. Because we're looking just at forces and moments and not stress, that's independent of the area calculation. So the weld stress results are going to be independent of the singularities. The next benefit, so there's numerous well-established standards out there that give you allowables for the nominal stress approach, right? The challenge here is we could simulate, let's say we have amazing hardware and we can model weld explicitly in everything we do and mesh them incredibly finely, right? We could simulate that, run it, and then the question comes back, once you query the weld stress at like a weld toe or something, what's allowable, right? And there are other standards out there that define allowable for like the hot spot method or other things like that. But from the standpoint of the nominal stress method, typically the standards we're looking at are going to be AWS D1.1 or DIN EN 1993-1.9. Both of these have a very similar approach to how they define allowable stresses and fatigue curves for different types of welds. The fourth benefit is this method works for both solids and shell bodies. So it's slightly more cumbersome to explicitly represent welds with shell bodies. So it's a benefit that this can work even if the welds are not explicitly represented. So the cons, some post-processing is required once the simulation is solved. All right, so if we solve our simulation, then we have to go in, extract those forces, calculate the weld stress, compare that to allowables, and then justify whether or not it's acceptable. And the second con is if we're looking at a long weld, some engineering judgment is required, because generally what you're doing when you do the nominal stress approach, you're defining usually the worst case section of a weld that you want to extract the forces from. The idea behind the nominal stress approach is the forces in the moments that you extract are kind of smeared throughout the defined weld length, and then you're going to use that smeared approach, figure out the worst case stress for that weld length, and go from there. The rationale being that essentially weld immediately next to each other will help participate in resisting some of the load. So that being said, if I have let's say an 8 or 12 inch weld, and I'm applying load to a welded plate, it's probably unlikely that let's say I have a hot spot at one end of the weld and the other side of the weld has very little stress. It's unlikely that the other side of the weld is helping that hot spot be resisted to any great extent. So this does require some amount of experience and some amount of engineering judgment. As is standard in any FEA, if it's unknown how long to go, it's typically good to go less, typically good to go more conservative. So focus more of the worst case load in a smaller weld length. Okay. So the nominal stress approach, I've outlined this a couple times. I'll go through it once more. So essentially, as we go to set up our simulation initially, we want to set it up so that parts are joined at welded locations. So there's several options of how to join parts, and I'll touch on those. Once we run the solution and solve it, then we want to extract forces in moments at the weld interface about the weld centroid. Part of the process within Mallett's method here is we always ensure that we set coordinate systems at the centroid of all the welds, and we orient those coordinate systems to coincide with how we typically do the weld stress calcs, right? So you'll see in a sec, usually we have defined coordinate systems relative to the weld cross-section, and so we have to make sure our coordinate systems are oriented the same way. Otherwise, we're going to get non-real results. So then step 3, so if necessary, we will then adjust the extracted force and moment magnitudes to compare to the appropriate code. Generally, really the only time we see this here at Mallett is if we're comparing to a fatigue case to AWS D1.1, because AWS D1.1 uses a stress range, and what we extract from ANSYS is a stress amplitude, right? So in that case, we need to double the amplitude to get the stress range so we can compare it accordingly. And then 4, so we use kind of our known weld geometry characteristics to calculate the weld stress, and then back compare that to the allowable stresses. Okay, so how can welds be represented in FEA, and particularly in this case in ANSYS? So there's a few different methods. So first, we could, as I've discussed, we could explicitly model the weld. That is an option. The second method is we could explicitly model the weld and just join it so everything is one body through that weld, right? The second option is if we have the weld explicitly modeled, rather than joining it directly, so it's all one body, we could bond bodies at the weld lines. Oh, sorry, I misinterpreted that. So the second is, rather than explicitly modeling the weld, we can just bond bodies at weld lines using ANSYS contacts, right? So if we're bonding solid bodies together, we have to bond surfaces, right? Because if we just bond a line, we still have degrees of freedom for that body to move in. It doesn't actually represent the rigidity and the restriction that the weld would impose. And if we're bonding shell edges or shells, we just have to bond edges because nodes on that edge will have restricted rotations and translations. And then the third approach, and this is really kind of our recommended approach here, is to assign shared nodes at all weld lines. The way that we can do this is within SpaceClaim, there is a feature called shared topology, right? This is a very easy way to instruct the ANSYS mesher to share nodes at certain interfaces. So the benefit of this approach is it's a very efficient way for model setup. Here we've had welded assemblies where we have hundreds, if not a little over 1,000. I think the most I've done is a little over 1,000 welds. In that case, I don't want to have 1,000 contacts in ANSYS that I have to define and double check, right? So it's much more safe from an error perspective and efficient to use the shared topology method. Another benefit of this is it reduces the number of stress singularities in the model relative to the bonded approach to number 2. And the one drawback, there may be others, but the one drawback that I really see in this approach is that it does require a APDL script to extract weld forces and moments. Essentially, you can no longer query the junctions. You actually have to extract those forces via script. So I put together a quick demo of just different ways that we could represent this. So here I have the exact same body represented 6 different ways. In the top right, this body is just going to be bonded at the interface. The next one over, you can see the fillet weld is actually physically represented, and it's going to be bonded to both sides, to the base plate as well as the vertical column. We have in the bottom left, similar setup. However, in this case, we have shared topology. So I'm going to have shared nodes along this interface. And then bottom middle, this is the top column. This is all one part. And then I have a bond through that interface just at the weld location. And then the two on the right, I just have this system converted to shell elements or shell bodies, surface bodies. And so for one, I'll just bond it at the interface with an ANSYS, and the other I have shared topology at that interface. So you have a lot of options in terms of how you want to represent welds. Based on ease, based on safety and quickness, we almost always go with, as long as the bodies in an assembly are the right thickness, the width to length ratio, and they can be shelled accurately, we'll always pretty much go with the approach to the bottom right, which is extracting surface bodies and then joining surface bodies with shared topology and shared nodes wherever welds occur. Okay. So we've represented the bodies. We know we want to use the nominal stress approach. So the next question becomes, how do we extract those forces and moments? There's really two ways to do it, right? So if we go with a bonded connection scheme in ANSYS, where we actually go in and establish a bonded contact for each weld, then we can use the ANSYS post processor to just query the forces and moments at that contact, and then do our stress calculations on that. The challenge here is ANSYS does support this capability in like static structural and transient structural simulations. However, for modal superposition analyses, so that's going to be harmonic analyses or random vibration analyses, that query option is not available. So for those types of analyses, we almost have to go to the second option, which is the shared node option. And you can actually use the APDL script extraction method for non-shared nodes for like bonded contacts, but at that point you might as well just do shared nodes. So the script that we have here at Mallett does rely heavily on the *get command as well as the fsum command. And that essentially what it does is if we were to, at a junction, query the forces and moments at that junction and extract the forces and moments, by default we get 0 force and 0 moments, because let's say for a static structural analysis, our structure is going to be at static equilibrium, so there can be no residual forces in the body. What the script does essentially says, I want to extract the forces and moments on one side of the connection, right? And so that breaks out that piece, and so we no longer get a 0 force and moment result, and then we can compare that to, or we can use that to calculate weld stresses. The one caveat here is, and I'll show this in a second, if we're going to, for either of these methods in the output controls, we have to turn on, by default, these are not turned on, we have to turn on nodal forces, right, because we want to extract these forces. And then for method 1, we need to turn on contact miscellaneous outputs as well. And that's just in the analysis settings, and I'll show that in a second. So I can show that real quick right now. So where I was just talking about is we just want to turn on our nodal forces and then our contact miscellaneous, just so we can actually pull out the information we want to. So in this case, I have the geometry I represented prior. I've applied the same force to the top of them. I've fixed all the edges on all the base plates. And then I've run the solution, right? So we can see we get a very similar stress response across all the base plates. And I can show you, if I zoom in, right, on a number of these, we can see that we do have, even when the welds are explicitly represented, we'll have a stress concentration at that weld junction. We'll have one down lower. We're going to have one right here. Essentially, it's just nearly impossible not to have a stress concentration, or not a stress concentration, sorry, a stress singularity of some type when we're looking at welds. So that being said, these are represented, right? For the bonded cases, I can just go in and create a force reaction query, right? Force and moment reaction query or probe, and just directly extract those forces and moments. And so you can see here, I have forces equal to the force applied, and then I have moments that are as expected. And I've gone ahead and done that approach for all of them. So I have my four ones that use ANSYS contact, and then I have my 2 others that use shared topology. And the result of that is that essentially I get nearly the same answer for each weld representation approach, right? So even though I don't represent the weld explicitly, in all cases, I still get nearly the same force and moment response, which is good for us, right? Because that's really all we're interested in, because we're going to take those force and moments values and then apply those to the weld characteristics. Okay, so then if we have these weld stresses, or weld forces and moments, how do we go ahead and calculate these stresses? Right, so this is just a screenshot of our kind of in-house weld stress spreadsheet that we use. So essentially, whenever I'm looking at a weld, inherently I know, because I developed the model and I extracted the forces and moments at a specific location, I know what type of weld I'm looking at, and I know the shape of the weld cross-section. So for this example, I'll be looking at a channel weld, right? So I have my channel weld. When I did my moment and force extraction, I set up my coordinate system at the centroid, oriented the same as shown here. And then I've started with my weld stress calculation, right? So first things first, I kind of have to determine my geometric characteristics, right? So that's just dimensions of the weld length as well as moment of inertia values. All right, so for standard welds, these values are generally tabulated in textbooks and online. This is just a small subset of different weld shapes that are possible. So if you have these tables available, you can just go in and grab the geometric characteristics. If you do not, you can do the math yourself, right, using these formulas and some integration to calculate the weld characteristics, so then you can go on to calculate the weld stress. So this approach here I'm outlining really just follows standard textbook like hand calculations for weld stress. So once we go through that process, we have our weld characteristics, those are defined. Okay, and the one thing I want to touch on that is important is this throat effective size, effective throat size. So knowing this effective throat size, and this is impacted by the type of weld, right? A full penetration weld of the same size as a fillet weld will have a different throat length. Knowing this dimension will have a large impact on weld stress results, because essentially your weld stress is going to vary linearly with the effective weld throat. So from a weld throat perspective, as we kind of go through this thing, for full penetration welds, it's equal to the full penetration part thickness, right? They're going to be the same size. Fillet welds are typically 0.707 times the weld leg size. Bevel groove welds, right? This is dependent on a number of factors. AWS defines this nicely for us. This table below is just an excerpt from that standard, where depending on the weld process used, depending on what type of bevel weld it is, and the radius of the associated plates that are being welded, we can determine our effective throat size to use in our hand calc. Okay, so once we establish that information, then we have our extracted forces, right? And in this case, we're going to just input into the spreadsheet. But we have our extracted forces, input in our spreadsheet. That goes through a number of calculations. And particularly here, we're looking at locations 1 and 2, because for this method, we extract the forces and moments. But then when we're doing our weld stress calc, we're looking for the worst case weld stress on the body that we defined. And so here we know that that's going to occur at locations 1 or 2. And so from there, we're just going to go to calculating the weld stress, right? The method we use to calculate the weld stress, this is taken directly out of a textbook. essentially we make the assumption that all loads, and it's on a fillet weld, it could be also applied to like a full penetration weld or a partial penetration weld or bevel weld, or et cetera, et cetera. We make the assumption that all loads acting on these welds are shear forces and occur on the critical section, which is the weld throat. Now this is a conservative assumption, but from our standpoint, typically when Mallett's doing work, usually we're verifying design robustness relative to like a test, and so we always are on the side of conservative rather than aggressive. And so just following that hand calc process laid out in this slide, which I'm not going to go into detail, we get a resultant stress. So here I have 3 sigma stress shown. So this would be for like a random vibration calculation. This just as easy, using the exact same process, it could just as easily be a max weld stress for like a static load case. The reason this is 3 sigma is essentially when I extracted my forces, there were 1 sigma forces and moments, and I had multiplied those by 6 to get my 3 sigma stress range, right? So I multiply it by 2 to get from stress amplitude to stress range, since I'm comparing to AWS, and then I multiply it by 3, so 2 times 3 is 6 to get my 3 sigma stress range. Okay, so now we have our stresses. So what's the next step? So the next step is you have your stress, you're going to compare to allowables. So generally, you're going to kind of look at 2 different stress allowables depending on what type of load case you're looking at. You're either going to be looking at a max allowable stress. That's usually for static loads, shock loads, things of that nature. Or you're going to be looking at a fatigue allowable stress. And so that's for fatigue loading, right? And so AWS, and that's really what we here at Mallett always default to, has allowable stresses for both of those cases. And just a quick note for background. So AWS was originally developed to work with hand calcs, and so it's well suited to work with this nominal stress approach, where we just get the forces and moments out. Okay, so max allowable stress. So just a brief overview of how AWS defines this. From a worst case allowable perspective, AWS essentially says your allowable max stress is 0.3 times the tensile strength of the filler metal. So it's fairly conservative, right? Via testing, it is known that this approach is generally has a safety factor of 2.2 or greater. So generally, if you have a safety factor requirement, usually you apply that 2.2 and then apply your safety factor to knock that back down. So usually when I'm doing an analysis, generally I have to assume worst case, because usually I have multi-directional loading. Whereas this table obviously has, if you know that you have primarily one type of loading, then you potentially could loosen up those requirements a little bit. But for multi-directional of similar amplitudes, it's safest just to go with the worst case allowable. So that's the max stress approach. Those are pretty straightforward. The fatigue allowable weld stress is slightly more complicated. So essentially how AWS handles this is they have a number of defined cases, and I've shown 4 here. There's many more than 4. And for each case, the case has different weld types, different loading conditions, different locations on the weld, things like that. It defines a fatigue strength, and it defines a stress category. So that stress category relates to the fatigue strength, which relates to a SN curve in this standard. And I will say this does require engineering judgment of what category to pick. It's not always clear right off the bat. So once you do figure out the category, that will direct you to a specific SN curve. And using the SN curve, we can make an estimate of total life. So there is a question that does often come up, right? So very often we see stresses that are above the fatigue strength. right? So what do we do with that? Because essentially this indicates we no longer have infinite life. Failure will occur at some point. How do we quantify that? So the caveat here is we most often see this at Mallett when we're simulating test conditions. So typically when we're simulating test conditions are meant to represent, let's say, 20 years of life in a 5-hour time span. So you have vibration levels that are significantly higher than would actually occur in operation. So to find or require yourself to have infinite life for a test case generally means that the structure is significantly over-designed, right? Generally that means that, hey, I'm saying that this can essentially survive forever, right? Whereas oftentimes we want to optimize our design and we want to make sure it passes tests so it survives a 20-year lifespan that is needed. But we don't necessarily want to make sure it survives 100 years because that may be unreasonable. There may be other factors that makes that non-feasible. So all that to say, to determine the impact of stress levels above the fatigue strength, we just step into Miner's rule. So, and if you're not familiar with Miner's rule, essentially it's just a cumulative damage rule. It's been around for, I want to say almost 80 years at this point. It essentially says that if I look at the number of cycles I expect to occur over the maximum number of cycles that would occur prior to failure, and I take the division of that and summation of different load cases, and if I look at the cumulative damage from all those different load cases, right, so you're going to get factors for each load case and you sum them together. If that cumulative damage is below 1, then my structure is safe. If it's above 1, it's going to fail, right? And generally, let's say I have I go through my random vibration simulation, extract the forces, do all the stress calcs, and go through Miner's rule and find that I have a cumulative damage factor of 0.5. That's equivalent to a safety factor of 2, or if the test I was referring to is 5 hours long, that essentially indicates that, hey, your structure is going to survive for 10 hours in the test conditions. Okay, and so the one note here is that if you're looking at fatigue analyses based on vibration loading, the one piece of information you need to know as well is the frequency at which that vibration occurs, right? So it's called the crossover frequency, and knowing that will allow you to calculate this small n value, so the number of predicted cycles. And then this is just a quick spreadsheet showing that resulting calculation. So I have my 1 sigma stress, I have my crossover frequency, I have my 5 hours. So it's really 20 hertz, so 20 cycles per second for 5 hours is going to give me a certain number of cycles. And just based on my probabilistic distribution for random vibration, I have a percentage of time for each 1 sigma, 2 sigma, or 3 sigma that stresses are going to be below my stress range value. From that, I can calculate the small n value with the crossover frequency. And then I can take my big N from the stress strain curve, or not the stress strain curve, sorry, the SN curve. This is just directly looking at if I have this stress, how long would the structure survive? And that gives you the big N. And so then small n divided by big N gives you your cumulative damage, and then you sum them together to get the total damage, right? And in this case, I'm seeing cumulative damage of 0.15, which is equated to a time to failure of 33 hours for this test case. So that should be it. So that was a whirlwind walkthrough of kind of Mallett's approach to weld stress analysis and fatigue for welds. So once again, it really just brushes the surface of what's available and what's known in the field. It's certainly not the only method. It's certainly, I'm not going to say it's the best method. right? It's a method we use here and that we've found to be generally successful and good at predicting failures, right? There's been cases where we've predicted failure and failures have occurred that have kind of justified this method in our minds. So I'll leave it there, and then I will open the floor to, does anyone have any questions? Okay. Well, if there's no questions, I can turn it back over to Boz, and do feel free if you do come up with a question in the meantime. You can always send Boz an email, all right, and then we'll get back to you.
Thank you, Steve. And thanks everyone for attending. Again, we'll have the next week's subject will be on meshing. And I'll send out an invitation to anyone on that. As always, feel free to forward that invitation to anyone that you think would be interested in it. We welcome anybody, even no matter how new they are, to ANSYS. I did record today's session, so if anyone would like a recording of the session, let me know, or if you know somebody that wanted to attend that couldn't.